Okay, in this segment, we're going to be starting to talk about approaches to nonlinear circuits. So how do we analyze nonlinear circuits? Well, in general, there's two approaches. One is called large signal analysis, and this is really use nonlinear models that characterize the devices and Kirchhoff's laws to solve for the desired relationships. So this is basically, you just see what you can do. There are some cases where the math is tractable and we can actually make some headway. In some cases, we may need to make approximations, and we can get models that are valid sort of piecewise. So in one region, we follow one equation, and in some other region, we follow a different equation. The other type of analysis that we often will do is called small signal analysis. Or sometimes incremental analysis. And in this case, what we're doing is we are linearizing the nonlinearities about a so-called operating point and using linear circuit analysis methods. And so the idea here is that if you have some sort of nonlinear characteristic, let's say, we'll talk about this in more detail, at some operating point, if this is, let's say, I, the IV plane, there's some value of I and V, which is the operating point. So there's some value of V, I, that your circuit is sitting at under resting conditions. And as the voltages and the currents wiggle around, they're not changing by very much. And so the idea here is that you can approximate this nonlinear current voltage relationship with the slope of the tangent line. And you can basically say that, well, if I'm not going too far, that curved line can be well approximated by a straight line, and I have sort of an incremental Ohm's law. And how big a small signal is will depend on the details of this nonlinearity, whether it's a very steep curve or if it's a very shallow curve that's changing, over a very, very at a slow rate here or a fast rate. So for some circuits, a small signal might be, a volt or a few tenths of a volt or something like that. For other circuits and other types of nonlinear elements, a small signal might be only a few millivolts. And to some extent, it also will depend on how much distortion we can tolerate. And so this division between large signal and small signal analysis is somewhat fuzzy and context dependent. But the basic idea here is that here we're using the full-on nonlinear models of our devices and applying Kirchhoff's laws and trying to do whatever math tricks we can to deal with the math. And here we're basically saying we're going to squint and assume that we're not changing things by very much, so that we can basically, you can think of this as expanding the IV relationships in a Taylor series about this so-called operating point. And we're going to basically say that all of the second order and higher terms in that Taylor series expansion are negligible compared to the constant term and the first order term, which gives us the increment. And we're just going to truncate the series after that first order term and assume that we're not going outside of the boundary where that approximation is good. And then we're basically treating the system as a linear system. And that's sort of the difference between these two approaches. And so I'll develop some of the concepts that we're going to be using for incremental analysis. And in some of the labs and in future weeks we'll be looking at some examples where we can actually do some large signal analysis to characterize our circuits. So let's suppose we have a nonlinear device. So let's assume we have some sort of device inside this blob, which we'll call X. And there's some voltage across here and some current flowing into the positive terminal. And the same current flows out of the negative terminal. And we can imagine driving this in one of two different ways. Right? So we could imagine a scenario where we are connecting, let's say, a voltage source up to our device. And then the current results. Or we can imagine having a current source connected up to our device, and in that case it's the voltage which is sort of the dependent variable. So here we might talk about the IV characteristic, and there might be some curve that looks maybe it looks like, I don't know, like that, where we could say I may be given by something like IS times F of V over Vs, where IS and Vs are scaling current and a scaling voltage. And these are device parameters, so-called device parameters. So that this function f is the function of a dimensionless quantity and returns a dimensionless thing, a number, and then it's scaled by IS to make the units work out properly. So this is a current and this is a voltage. And if we drive it this way, we're talking about maybe some kind of VI curve. And since it's the same device, it's really the same VI curve, really the same same type of behavior, it's just we're looking at the inverse function. Something like that. And here, V would be Vs times F inverse of I over Is. Okay, it would be characterized by the same scaling voltage and the same scaling current. It's just that these two functions would be inverses of each other. Okay? So that's kind of what we're talking about here. Two different ways of driving it. And conceptually, this experiment here would be what we would see in an IV plot, and this experiment here is what we would see in a VI plot. So here the current is the independent variable and the voltage is the dependent variable. Here the voltage is the independent variable and the current is the dependent variable. And if we think about an operating point, which is some particular value of I and V, that defines some point on this curve that the circuit is currently located at. So this is, let's say, I0, V0. So that same operating point lives on this curve. And what we're going to use to characterize this type of device is, like I said, the slope of the tangent line to this characteristic. So the slope of this tangent line here is going to be called Gx, which is the partial derivative di dv evaluated at V0 I0. And the slope of this tangent line here is r sub x, where r sub x is dv di evaluated at that same point, I0 V0. And of course, by the inverse function theorem, we have that basically g sub x is equal to 1 over r sub x. Right, if I take the inverse of this curve, I just flip the axes around, the slope of this tangent line just gets inverted. So what these parameters really tell me is if I increase, let's say in this situation, if I increase v by some little delta v, I will increase by some little delta I. And here, the delta I is approximately given by Gx times delta V. Right, so the delta I is given by an incremental Ohm's law. Here, if I increase I by some little delta I, V will increase by some delta V, and the delta V will be approximately equal to R sub x times delta I. So the incremental conductance, this is incremental conductance, and this is incremental resistance. The incremental conductance tells me, for a given device, if I change the voltage across the device by a little bit, how much additional current is required by the device. And the incremental resistance basically says if I increase the current into the device by a little bit, how much does the voltage have to change in order to let that extra amount of current in? Okay, so these are incremental Ohm's law. It's basically like saying, gx, which is really formally the partial derivative, dv di, is approximately equal to the finite difference delta v over delta I. And strictly speaking, if you take the limit as delta I goes to 0, that finite difference quotient approaches this partial derivative. And r sub x is basically this is di dv. di dv, which is about delta v, delta I over delta v. And this is dv di, which is approximately delta v over delta I for sufficiently small delta v and delta I respectively. Okay, so these are the concepts that we're going to use to characterize the behavior of a nonlinear device in the vicinity of some so-called operating point. And incrementally, we're going to assume that the change in the voltage is proportional to the change in current, or vice versa, through these incremental conductance or incremental resistances. Okay, so we want to see some things about how these incremental properties of nonlinear devices combine with each other for devices connected in parallel, for instance. How do these incremental properties behave? So how about nonlinear devices in parallel? Right, so here, suppose I have, I'm driving, let's say, with a voltage. And we got two devices, X and Y. Connected with each other in parallel. And I've got some voltage here, V, Vn, In. I've got Vx and Vy. And there's some Ix and Iy. And what we would like to know is, if I increase the V here by some delta Vn, that'll make In go to In plus some delta In. What is, say, delta In? How are these delta I how are delta In and delta Vn related to each other? If we know something about the incremental properties of X and Y. So we're going to assume that X is characterized by some Gx. So X characterized incrementally by Gx, and Y characterized incrementally by Gy, so that we know that Ix, or that delta Ix is approximately equal to Gx times delta Vx, and delta Iy is basically given by Gy times delta Vy. Well, we know, for instance, that KVL, which still holds for nonlinear circuits, tells us that Vn is equal to Vx is equal to Vy. And KCL, which still holds, tells us that In is equal to the sum Ix plus Iy. Well, I can differentiate the KCL. With respect to Vn. That tells me that din dvn is equal to d by dvn of Ix plus Iy. Well, derivative is a linear operator, so this is equal to dix dv in plus dix diy rather dvy or dv in. And because of KVL, this is equal to dix dvx. If we substitute in vx for vn, plus diy dvy. We substitute in vy for vn, and this is just equal to gx plus gy. And this is really din dvn is really gn, the equivalent conductance, or GEQ, right? The equivalent input, incremental input conductance of the parallel combination. Or maybe I should say it's GEQ. So what we have here is basically the notion that, like conductances connected in parallel, which just add to get the equivalent conductance of the parallel combination, if I have incremental conductances of two nonlinear devices connected in parallel with each other, those incremental conductances just add. And if I like, I could take this a step further and say that since these incremental resistances and incremental conductances are related to each other through the inverse function theorem by a reciprocal relationship, this implies that 1 over Req is equal to 1 over R sub x plus 1 over R sub y, which implies that Req is equal to reciprocal of 1 over Rx plus 1 over Ry, which is just Rx parallel Ry. Right, so the incremental resistances combine in parallel just like you might expect. Okay? I should have said that there's some increase in Vx here, and some increase in Vy, some increase in delta Iy, or rather delta Ix, and some increase in delta Iy. When I increase Vn, there's some increase in the voltage across both of these devices, which is the same, and some increment in Ix and some increment in Iy, and that those sum together to form the increment in In. That really leads us to our next thing, which is, how does this current delta In divide up between x and y? So we have an incremental current divider here. Right, so how about that? Incremental current divider. Well, this stuff is still true, and KVL incrementally also implies that delta V in equals the delta Vx equals the delta Vy. KCL incrementally implies that delta I in is equal to delta Ix plus delta Iy. And you can show these incrementally by just taking the before KVL and the after KVL and subtracting them. And you can take the before KCL and the after KCL and subtracting them, and you get these incremental KCL and KVL relationships that hold among the changes. Okay? And we can apply our incremental Ohm's law here. So if we want to know what is delta Ix, well, delta Ix actually, for the current divider situation, we want to know what is delta Ix over delta In, right? And we can get that pretty directly. So we know that delta Ix from incremental Ohm's law is just equal to G sub x times delta V sub x. And we know from the equivalence that we just showed, that delta In is basically given by Gx plus Gy times delta V in. Right, that's incremental Ohm's law for our parallel combination. And since we know that delta Vx is equal to delta In, or delta Vn, we can just divide these two equations. And the delta Vx's cancel, and we're left with delta Ix over delta In is equal to G sub x over G sub x plus G sub y, or delta Ix is equal to delta In times the current divider ratio, or incremental current divider ratio, Gx over Gx plus Gy. And this is exactly our two-way current divider, with a current divider ratio expressed in terms of conductances. So this is a current divider. Incremental current divider ratio. And of course we can express this in all the same ways as we did the regular linear current divider. So we can express this in terms of Gx, or rather Rx parallel Ry divided by Rx. We can also express it in terms of the incremental resistance of the opposite branch, Ry divided by the sum of the two branch incremental resistances, Rx plus Ry. Of course, G, we can do the same argument with delta Iy and find that delta Iy is given by delta In times Gy over Gx plus Gy, or Rx parallel Ry divided by Ry. So the incremental current divider works exactly the same way as the regular linear current divider. Incremental resistances combine just like regular resistances. Incremental conductances combine just like regular conductances. And so the take-home message is all of the machinery of linear circuit analysis that we have been talking about and you've learned about before will also hold for this sort of incremental or small signal analysis for small changes about whatever operating point the system is currently at. Okay, so that's all for this segment, and we'll see you next time.